today's lecture, what we are going to take up is a design example on an isolated footing. Now, when we take up an example on an isolated footing could be a square footing, it could be a rectangular footing. For In this question, we would be taking up a rectangular footing. Its example. Let's uh, design an isolated footing for let's say there is a column which is which has got dimensions for 500 cross 500 mm. These are the dimensions of the column. And next, we also know that the bars are 8 mm phi dia in footing. Now, whatever is we are using 8 mm dia bars and load of 3000 kilonewton. It's a working load is acting on the footing. Now, this is the load that's acting on the footing. Let's say there is a bearing capacity of the soil is 50 kilonewton per meter square, right? That's the bearing capacity. Now, the bearing capacity is all usually at a depth of 1.5 meter below the ground level, where we actually determine it. This is the usual depth. We're going to design this footing in M20 grade concrete, and we're also going to use Fe415 steel, Fe500 steel. So this is the question. We have to design an isolated footing for a square column. Now, something other information, like if you have a square column, you would normally go for a square footing. But let's say there is a restriction on one side of footing is 2.5 meter in length, so you would usually have to go for a rectangular footing in that case, because a square footing would not be feasible. Now, what is the load that's acting, the working load that's acting on the footing? That's 3000 kilonewton. And what's the bearing capacity? 150 kilonewton per meter square. These are two very important parameters that we need to first of all check. So let's go one by one. What's given to us? One, it's given that there is a load of 3000 kilonewton. That's given. Next, what is given is that the allowable it's not allowable, this is the bearing capacity, but this is safe bearing capacity that's given in the question. So let's change this here. This is safe bearing capacity. So once we say safe bearing capacity, that means the QA value is 150 kilonewton per meter square. This is the value of QA, and this is at depth h of 1.5. And now if P is 3000, what's delta P? Delta P would be 10% of 3000 kilonewton. So overall, this would be 3000 plus 300, that's 3000. So total P plus delta P is 3300 kilonewton. Now, what would be the area? That's step number one. Determining area and dimensions of footing. So let's fix the area first. We can get the area of the footing in the initial phase. Now that is A. Area A would be, because we know, let's do this like this. QA is P plus delta P, and this whole divided by A. So A value would be P plus delta P is 3300 cross 10 raised power 3, that's 1000, uh, divided by, so the area of the load is 3300 kilonewton, that's 3300 cross 1000 newton divided by, now QA is 150 kilonewton. uh, let's change this as well, so that would be into 1000. So the area that we are getting is how much? 3300 divided by 150, that's 22 meters square. This is the area that we are getting, the base area that's required, that's 22 meters square. Now the dimensions, how do you obtain the dimensions of the footing? This is very important. If you have 22 meters square and one of the sides is restricted to 2.5 meter, let's not restrict it to 2.5, let's change the question. Let this be restricted to 4.5 meter. Let this be restricted to 4 meter, one of the sides, just in order to make a rectangular footing cushion. So say length cross breadth is 22 meters square, then say width is B is 4, then this would be, then the value of L would be 22 divided by 4, that's 5.5 meter. So we're getting a rough sketch of the footing. It's something like this, 5.5 cross 4. So one of the sides is 5.5 meter and the other side is 4 meter. Now we know there are, now this is clear that we are getting a footing of around 5.5 cross 4. Uh, shall we go ahead with this type of footing? The restriction is 4. Otherwise, you because the column was square, we could have simply gone for a square footing, 22 under root of 22, and that would have given us the square footing. So, what is the net soil pressure on the footing? We could go for areas greater than what we have provided here, 5.5 cross 4. So, net soil pressure would be, what's the total load actually onto the footing here? Uh, let's check. That's what was the amount of load that was acting? That was 3300. Yes, it was 3300, but that included the weight of the footing itself. So while calculating the net soil pressure, we do not need to add the value of the soil pressure. In calculating the soil pressure, we do not need to add the value of the soil self weight of the footing as well. So this would be 3300, right? Sorry, this is just now 3000 is the total load that was acting, divided by what is that we are providing, 5.5 cross 4.0, and let's factor this out to 1.5 in order to get the net soil pressure in terms of the factored soil pressure. So this would be 3000 cross 1.5 divided by 5.5 divided by 4. So that's 204.54 kilonewton per meter square. So what we are actually getting is a actual soil pressure, a net soil pressure that would be acting onto the this footing. So let's now check if we are providing a footing. Say this is 5.5 meters side of the footing. The pressure on the footing is at any given point is, now you don't need to confuse this with the bearing capacity that this would fail. No, this is the pressure exerted on the footing, not on the soil. This is the reaction offered from the soil onto the, for which we are designing. So if this is 1 cross 1 meter cross 1 meter, then in that case this portion would be loaded by 204.54 kilonewton per meter square. So that would be the pressure exerted on this portion of the soil. So this is the actually the soil pressure exerted onto the footing from the soil onto the footing. So thereby at this stage we are clear with whatever is the load that's being acted on the footing. We can even convert this. This is 0.204. Uh, let's keep it to three decimals. Newton per mm square. It's into 10 raised power 3 divided by 10 raised power 6. So you're getting net 10 raised power minus 3 to that, and so you're getting 0.204 Newton per mm square. Now we have fixed the dimensions, the length and the breadth of the footing, and we have calculated the soil pressure that's exerted onto the footing. So next we'll be determining the thickness. Step number 2, thickness of the slab or the footing, the footing. This will be based on shear criteria. So at this stage we are now clear that what is the thickness of the mm, how do we calculate the thickness of the footing. Now how do we calculate it? In the last lecture towards the end we discussed one-way shear and two-way shear. These are the two methods by which we obtain, on trial and error basis, we are actually going ahead with calculating the thickness of the footing. So it's either of the two, the one-way shear or the two-way shear, that dictates what would be the thickness on of our shear of the footing. So uh, if I first of all begin assuming the thickness of the footing uh, by any some value, then I can proceed with calculation of the shear criterias, and if they are within the check or within the control, and also uh, there it's not too unconservative, then I will retain the same uh, thickness. Now if it's becoming too conservative, then I'll decrease the thickness, and if it's becoming uh, on the uh, that is it's failing in shear, so we need to again revisit the thickness. So what we'll be doing is, usually uh, this is a thumb rule, while you are designing a footing, you can start with the 300 depth footing, an isolated footing, and you can go on. For simplicity's sake, let me at this stage and take a 500 thickness. That thickness of the footing be 500 Let this be 500 thickness. Uh, then in that case, this is the overall thickness of the footing. The cover uh, is generally taken as not less than 30 So for footings, uh, but it's usually taken on the higher side. Let's take 75 cover. That's a clear cover for the footings. Let me show you the code which meant for this. So this is the minimum cover that's given for footings is 50 mm. This is clause 26.4.2.2 given in the code. So it's not 30 mm. Its minimum is 50 mm that you use for calculating the uh, cover for the footings. So we'll be going for 75 mm, which is less than greater than 50 mm. So you are meeting that clause. Next, uh, once you have already determined the clear cover, let the reinforcement used is 20 mm. We probably mentioned 8 mm in the question. So let's forget about this, that this is not given in the question. The 8 mm would be quite less for this type of a question. So this information is not provided to you. So let the reinforcement used is 20 mm bar dia, and this would be usually in the longer direction that we provide 20 mm. So you would also have the reinforcement in the shorter direction, and that would be lesser, because we that side becomes in short direction is say 16 mm. That side becomes the secondary reinforcement. The primary reinforcement here is in the longer direction, and the shorter direction we are using some 16 mm. So thereby uh, it's now clear, if one has to determine the effective length, effective depth of the footing in long direction, in that case, what would be the, yes, what would be d along x along the long direction? It would be 500 mm minus the cover, that's 75 mm is the clear cover, and then you have the reinforcement, which is 20 mm, but we would be taking uh, half of the 20 mm. So overall this would be 415 mm in the long direction. Then the effective depth in short direction would be how much? If we calculate this dy, that would be again 500 minus. Now the main reinforcement which runs along the long direction is usually provided at the bottom, and the shorter direction reinforcement will be provided above it, in perpendicular and above it. So this would be 75 the cover, then 20 the longer direction reinforcement, and then half of the shorter direction reinforcement. So this becomes 397 mm. So now you have the effective depths. Uh, if you now take the average of both the effective depths, how much would that be? 415 plus 397, 2, that's 406 mm. is the average effective depth that we are getting from these two. Now let's begin with the one-way shear condition. What is the condition of the one-way shear? First of all, in a one-way shear, one needs to provide uh, the check the one-way shear at a distance of d from the face of the column. Now, what is d from the face of the column? So, if this is the footing and the column is this, now we know that this dimension is 5.5 total, and this is 4. Then the section at which the one-way shear becomes critical is at d distance on either side of this. Similarly on this side. Now, what is d distance? It's from the face of the column that it's at a distance of d. The face of the column is this. So now, if one has to determine, similarly in the shorter direction, it will again be at a distance of dy, but we would be calculating the one-way shear along the longer direction mostly, uh, because that would mostly become critical here as dx is greater. Let's check this. So dx is how much? Just let me recollect this. Dx is 415 mm. So dx is 415 mm. And that's the distance from this point up till this point, or on the other side as well. That's 415 mm. Now, at that section, what is the shear? Now, how do you determine the shear in this? Let's along the longer direction, the profile plane of this would be like this. On the foundation, that is how much? Let me go back. This, it's 0.204 Newton per mm square. It's 0.204 Newton per mm square. So if I have to determine the shear at this location, what do I have to do is I have to multiply this by, first of all, I need it along the UDL line, along this line. For that, I have to multiply it by the width. So shear would be this VU, the ultimate shear would be 0.204, that's Newton per mm square, cross how many mm's does this is this in the shorter direction? It's 4,000 mm. Why are we multiplying it by 4,000? We are concentrating all the load that's acting along the shorter direction onto a single line, this green line somewhere, and I'm getting that value cross. Now this would be the load, the total load that would be acting on that line. um how much would that be? Just let me first calculate that. 0.204 cross 4,000, that's 816 kilonewtons, no, newtons. It's 816 newtons uh, per mm square. It This would be now per mm, so it's 816 newton, that's 0.816 kilonewton per mm along this line. um, Along this line, 0.816 newton per mm. So if now I have to calculate the shear force along this line, where is it supported? Just tell me, where is this supported? It's supported at the center. Yeah. And what would be the shear force at the center where it's supported? The shear force, this is becoming a cantilever now. This has a cantilever action on both sides of the support. So the minimum shear force would be at the point of the maximum bending moment, that's at the free ends of this cantilever. That's so the shear force at those points will be zero, and the maximum would be at the support. So but now the support itself is a big entity. This is how much, uh, what is the size of the column? 500 cross 500. So this is 500 mm cross 500 in the other direction as well. So how much is this distance now? Right from here up till this point. Yes. How much would that be? Uh, what's the total distance? 5.5. That's 5,500. You just subtract 500 of the column, divide that by 2. So that's 2,500. So this distance is 2,500 mm. Now, where do I need the shear force? At a distance of dx, that's 415 mm. So I need the shear force somewhere here, which is at a distance of 415 mm. So at that point, the shear force at this point is 0, and its maximum at this point, it's increasing like this. It's at maximum at the face of the column, and we are taking it at critical at this point. How do you determine the shear force along the length of the column? Just it's W U into L at whatever point you need to determine it. So that would be the shear force at W into L here when you have a UDL load here acting. So this is what is L, that's 2,500 minus, you're determining at a certain value. Now X from the free end here, it will be 2,500 minus, yes, how much is that? 415. I'm determining the shear force at a distance x. This x is from here up till this point, and that would x is 2500 minus 415. So you are getting it as W into x. So thereby the value of VU is 0.204 into 4000. So this whole comes out to be 4000 cross 0.204. So this is 1701360 divided by 1000. That's 1701.36 kilonewton. So you're getting a value of VU equal to this 1701. Now, if I first of all check what was the what would be the shear stresses, that's tau. Let me first get the symbol. It's this tau of u would be equal to VU divided by B cross D or D. So that value is, we already know the value of the depth of the section, and what is the value of B, we already also know that. So VU is 1701.36 to 10 raised by 3 divided by B. What is the value of B? That's 4000, right? So this value is 4000. D, that's small d along this direction, dx, that's 415. So this we are getting as 0.00 Newton per mm square, quite a small value of the forces that are acting on this. So what we have now obtained is the value of tau V, the one-way shear force or the one-way shear stress that's acting on this footing. So thereby, first, yes, we need to check this for tau C, which is already given in the code, the values of it which you must have already determined while you were checking. Let me share this. So this is the value of tau C, and for different percentage of steel, right now we are using M20 grade concrete here. So what's the percentage of steel that we would be using in this question? And that's very important uh, to know what is the percentage of steel that we will be using in this question. Now, how do we get that? Because as of now, we are not aware of any such thing uh, about the steel that we would be using. So either we assume the percentage of steel at this point, or what we can do is that we can uh, s- based on this we say that our design criteria is right at this stage, and the amount of forces are quite less. So even if you are assuming, let's assume based on certain facts, uh, let's take a condition. For example, you have a 20 bar dia bar. Now if that is spaced, say at this stage, let's say at 100 we are spacing the 20 dia bar. So that would be 314. So that would be 3140 square of the bars that we are providing, uh, around that much amount of. So even if we, this is a rough calculation. So for every little cross section of this, that would amount to 0.001. That's just 0.2% of steel at maximum. 0.2% of steel. This is just an assumption at this stage. If we are providing 20 bars at say around 100 spacing, then that would be 0.2% of steel. So tau c in that case, for 0.2% of the steel, that's somewhere in between these two. For M20, it was between this and this. And because it's all based on the assumption, let's say this is between this and this would be around 0.34, 0.3. Let's take 0.34. Uh, let's be on the higher side at this stage. So this is 0.034 Newton per square. Now you already are seeing that tau u is quite less than tau c. So tau u is quite less than tau c. So it's okay. We do not need the shear reinforcement in this footing. That's one thing. The other thing is, when you are not requiring the shear reinforcement, uh, we are also trying to check what is governing. But for that, we need to first of all check uh, the uh, two-way shear criteria as well for this footing. So what we will be next doing is we'll be checking the two-way shear criteria. Uh, uh, so yes, we could also do the same thing for the other direction. That's the shorter direction. But one would naturally get that to be on the lower side. Why? Because first of all, uh, what would be, this would be greater. This would be multiplied by 5500, but this value 25 would be decreased to less than 25. So it's naturally becoming lesser than the this value. So the shear forces are quite getting even decreased on the shortest direction, so we do not need to calculate or check on that direction. So we next check for the two-way. On the basis of two-way shear, we're checking this section. uh, what for in that case, first of all we need to first of all check what is the criteria of the section in two-way shear. So if this is the footing and we have a column at this location 500 cross 500. Now a two-way shear usually occurs as a punching mechanism in this plane. Now this plane is at d by 2 on all directions. D by 2. Now that d by 2 is from here up till this point. It's from here up till this point. Similarly here and here and here and continue. So you have a circumference or a perimeter about which the two-way shear is a punching shear is acting onto this section. So we can easily determine the two-way shear criteria uh, along this critical section. How? We need to first determine what is the value of d. Now for first that would be here. In this case, uh, this would be at an average distance. What is average distance that we calculated? Let's go back. That's 406 mm. So d by 2 is 406 by 2. That's 203 mm. So this value is 203. Now, what would be the value of VU in the two-way shear case? What was the value of the forces? That was 0.204. It was Newton per mm square. Now, while you are determining the two-way shear, this is already in Newton per mm square. You now need to multiply it by the area about which this would act. Now, try to get this. The two-way shear is acting about this green line only, but it would be also acting along the depth of the green line. So the plane or the area of area section for this two-way shear is along the green line and along its depth. So I hope that you understand. It's like you have cut a cake, and whatever area you are getting on the four sides of the cake, that's the area that I am talking about. So that area will be getting exactly at the center of the shear force. Now, along the boundary, if I am taking that, now this is d by 2, this is d by 2, this one, then you have d by 2 here, and this is 500. So that's 500 plus 203 plus 203, that's 406 plus 500, 906 cross 906, other direction as well. So you're getting the shear force along that critical section. So the value that you are getting is This is coming to out to be 432.0549. This is in newtons. That would be 4320.549 kilonewtons. This is the value of shear force you're getting along this dimension. Then this is the two-way shear one is getting. So what is the value of two-way shear resistance? That's again given in the code. If you check this clause, 31.6, so permissible shear stress. When reinforcement is not provided, the calculated shear stress at the critical shall not exceed Ks into tau c. Ks is this 0.5 plus beta c, but not greater than 1, beta c being the ratio shorter side to the longer side of the column, and tau c is limit state, and this is when the shear stress at the critical section exceeds the value but less than. So that's for that case. So in our case, uh, when we are determining the critical section about this 15b, 15a, in that case we have to multiply this by ks in order to get the value of tau c. So v critical one would be ks into tau c or vc vc itself, but vc itself is tau c into uh, the value of what's the value of the area that's in around the section. How much would that be? uh, so usually we can just say it's ks into tau c, where tau c value is 0.25 into under root f ck. But do we know tau v at this stage? Yes, we know that. So this is, what's the value of ks? uh, what we just saw, ks is 0.5 plus beta c. Now beta c is 1 here for the column, short to longer side, 500 by 500. So but you cannot exceed this 0.5 plus 1 would be 1.5, but it does not exceed 1, so ks would be 1. So we have that value here, and tau c would be 0.25. So this is 1, and that's 0.25 of under root, how to write root here. Let's tau c is under root fck. Fck is 20. It's all raised by 0.5. That's root. So we're getting a value of root of 20 cross 0.25. It's 1.11. This is the value of, again, the value of tau c. Not, I'm just simplifying this. This is tau c. So you can just, in order to separate it, let be tau c dash. What would be tau v here? Would be 4320.549 10 raised by 3 divided by, what's b here? Uh, for this whole section, what would be b? B would be now the circumference uh, of this section. This would be total B. How much would that be? 906 into 4 into D. D is the depth. That's 406. So this value one is getting as 0.549 into 10 raised to 3 by 906 divided by 4 divided by 406. It's 29.56 Newton per mm square, which is far greater than what is available to us. So what we are getting is, I think I need to recheck this uh, because there is certain issue here. This would not come out to be this much. It's 2.93. This is 2.93. That's coming out to be greater than tau v is coming out to be greater than tau c dash. So we're actually getting tau v greater than tau c dash. That means this is actually failing in this direction. So you actually need to redesign for this criteria by taking a deeper section. So let's now take a deeper section for the, you only had two options in order to increase the value of this, decrease the value of tau v. Either you increase the uh, concrete its grade, you either do that or you increase the depth now of the footing. Now we had to increase the depth of the footing based on this criteria. Our initial thickness was 500 mm overall. Now let our overall thickness be 900 mm. Let's hope it is right this time around that we are getting. Then d by 2 would be, I'm just uh, rewriting over this. So let me use another pen here. So d by 2 would be 900 minus, uh, first of all, let me get the average out of the two. So in this direction, it would be 900 minus 75 minus 10. That would be, that's 815 mm. In this direction, it would be 900 minus 75 minus 20 minus 8. So that would be 900 minus 75 minus 20 minus 8. That's 797. Then one-way shear, we do not need to check that because it was already not failing even for that thickness. So now this would be d by 2 would be 900, sorry, not 900, this would be the average of the two. We calculate the average of the two. Average of the two is how much? 815 plus 797 divided by 2, that's 806. So average is 806 mm. So this is 806 divided by 2, that's 403 mm. So this comes out to be, this is same, this is same. So 906 is your d by 2 is actually changing now. That's 403 plus 403, 806 plus 500, that's 1306 in either direction. So this is coming out to be 1806 now. Sorry, 1306. I'm talking about this. This is 1306. This green line along both, right from here up till this point. Similarly, from here up till this point, it's 1306 each. So then you are getting this as 1306 cross 1306. So the value is coming out to be how much? Yes, it would be lesser now. 5500 in cross 4000 is 1306 cross 1306 is this much. Cross 0.204. This is 14 414005 44005 0 newtons. That is 4140.050 newtons. Hope this is okay now. Let me check tau v. Tau v would be 4140.050 cross 1000 divided by how much? This is not 906 anymore. This is 1306 cross 4 cross 1306. 403. Sorry. It's 806. This is 4140 6 divided by 6. So 0.98. Perfect. 0.98 Newton per. Yeah, you could have just kept it a slightly lesser depth than this, but this is almost okay. So less than 1.11, rather than what I did here by just guessing that I'll now not go for 500 mm, but rather for 900 mm. I think 800 mm would have been okay. So right now, let me go for 900 mm without thinking about any further about the economy. So this is okay. 900 mm overall thickness is okay for one-way shear. It's okay for two-way shear as well. So we have designed the footing now for three parameters. One is the depth, that that is now 900 overall. The dimensions, that's 5500 cross 4000. Next lecture we'll be talking about how to design the reinforcement for this section now.